In October 2025, a robot submarine scanning the floor of Lake Biwa, Japan's largest freshwater lake, found something that should not have survived. A pottery vessel, nearly intact, buried in sediment at the submerged ruins of Suzuraozaki, 64 meters below the surface, about 25 centimeters tall, with a pointed base and engraved patterns. Experts date it to between 10,500 and 11,000 years ago, more than 10 millennia underwater. 10 millennia underwater. Earthquakes, temperature shifts, constant water saturation, and the clay walls still held. That ceramic planter on your porch, the one you bought 3 years ago, probably already has hairline cracks running through it. Modern materials, modern kiln, modern glaze. The people who made the Lake Biwa pottery never built a city, never smelted metal, or never wrote a word down. They did not have kilns in any modern sense, and yet their clay lasted longer than almost everything you own. 16,000 years ago, Central Honshu, the main island of Japan. The last ice age is in its closing chapter. Deglaciation has begun, but the Pleistocene has not ended yet. Temperatures are still recovering from the glacial peak roughly 20,000 years earlier. Sea levels sit around 120 meters lower than today, according to ocean core data compiled by the Geological Society of America, exposing coastal plains that no longer exist. The archipelago is colder, drier, and in some areas still linked to the mainland by land bridges that will disappear within a few thousand years. Small bands of hunter-gatherers move through forests of oak, chestnut, and walnut. No farming. No agriculture for another 10,000 years, but they have fire. They have river clay. And at some point, in what radiocarbon dating from the Odai Yamamoto ice site in Aomori Prefecture places at approximately 16,500 years ago, with dates reported by the National Museum of Japanese History, someone shapes wet earth into a vessel and pushes it into the coals. A soft hiss, water escaping through microscopic channels. The smell is mineral, chalky. The temperature in those open fires reaches maybe 600 to 800 degrees Celsius, far below the 1,200 plus degrees of a modern ceramic kiln. The result should be fragile, porous, temporary. That is what most materials science would lead you to expect. And yet those vessels survived. Not hundreds, tens of thousands. Across every region of Japan. Across nearly every climate zone the archipelago offers. From subarctic Hokkaido to subtropical Kyushu. Jomon pottery spans roughly 14,000 years of production, one of the longest continuous ceramic traditions in human history. By the end of this video, you will understand the main material mechanisms researchers believe helped that clay last. You will see what Jomon potters did differently from most ceramic traditions that followed, and about 12 minutes from now you will see a comparison that should change how you think about the word primitive. But first, you need to understand why clay should have failed at all. Clay is not stone. That is the problem. Stone is a mineral structure locked into crystalline bonds by geological pressure over immense spans of time. Clay is what happens after stone breaks down. Feldspar weathers into kaolinite. Granite crumbles into montmorillonite. Large clay minerals are flat, plate-like crystals, some only nanometers thick, stacked loosely with water molecules wedged between them. When you fire clay, you are trying to reverse part of that decomposition. Heat drives out water and forces particles to bond more permanently. The technical term is sintering, particles fusing at contact points without fully melting. In a modern kiln, strong vitrification and the formation of high-temperature mineral phases happen above roughly 1,100 degrees Celsius. At those temperatures, silica and alumina can begin forming mullite, a mineral phase known for exceptional stability. Below roughly 1,000 degrees, substantial mullite formation is limited. The clay hardens, yes, but it does not fully vitrify. What you get is an open, porous structure riddled with microscopic channels, a sponge made of rock dust. Water enters those channels, freezes, expands by about 9% in volume. Ice wedges the particles apart. One freeze-thaw cycle does minor damage. 100 can start cracks. 1,000 can destroy the vessel. Jomon pottery was fired well below the temperature range associated with dense, vitrified ceramics. Open bonfires, no enclosed kiln, no precise temperature control beyond adding or removing fuel. By the expectations of later ceramic engineering, those pots should have been vulnerable, especially submerged in lake sediment where saturation is total and environmental stress continues year after year, 10,000 years underwater, and still, the clay held. The first mechanism is hiding in the clay body itself, not in how it was fired, but in what was mixed into it before firing began. Jomon potters added plant fibers. A lot of them. This is not just speculation. Ceramic petrography, thin section analysis under polarized light microscopy, reveals dense networks of fiber voids throughout Jomon sherds. Research by Shinya Shota and colleagues in Quaternary International in 2014 documented systematic fiber tempering across multiple Jomon phases, identifying both vegetal fiber impressions and the characteristic void structures left behind after those fibers burned away during firing. Here's what happens. You take river clay, fine-grained, plastic, sticky. On its own, it shrinks dramatically as it dries, sometimes 8 to 12% linear shrinkage. That shrinkage is one of the biggest killers of low-fired pottery. Stress fractures, invisible at first, catastrophic later, now knead in chopped plant fibers, grass stems, bark strips. The fibers do three things at once. First, structural mesh. The fibers distribute tension more evenly as the vessel dries. Think of rebar in concrete. Without reinforcement, concrete cracks easily under tension. Fibers in Jomon clay bridge across developing microcracks and help stop them from propagating. Second, controlled voids. When fibers burn away during firing, they leave behind tiny channels running through the clay wall. That sounds like a weakness. In this case, it may have been an advantage. Those voids interrupt crack propagation. Materials scientists call it crack deflection. A crack tip hits a void, loses energy, and has to restart on the other side in a new direction. A crack that would travel straight through solid clay gets slowed, redirected, exhausted. Research by Kilikoglu and colleagues in the Journal of Archaeological Science demonstrated through mechanical testing that fiber-tempered ceramics can show significantly higher fracture resistance, measured as work of fracture, compared to untempered ceramics fired at the same temperature. The fibers made the clay tougher, not harder. That distinction is everything. Hardness resists scratching, toughness resists breaking. A diamond is hard but brittle. Leather is soft but tough. Jomon potters appear to have been optimizing for toughness, the ability to absorb stress without catastrophic failure. Third, and this may be the most important part, those void networks gave the clay a critical thermal advantage. When water enters the porous structure and freezes, it needs room to expand. In a dense, low-porosity ceramic, there is nowhere for the ice to go. Pressure builds, the wall cracks. In a fiber-tempered body with controlled void channels, the expanding ice has somewhere to push into. The voids act like pressure relief spaces. This is not just a metaphor. It is the same general principle modern engineers use in freeze-thaw-resistant concrete. Air entraining admixtures, chemicals that create tiny, evenly spaced bubbles, were developed in the late 1930s to solve the same problem: roads and structures cracking in winter. The U.S. Federal Highway Administration still specifies air entrainment for concrete exposed to repeated freeze-thaw cycles. Jomon potters reached a functional equivalent with plant fibers roughly 14,000 years before anyone formalized the physics. Studies of Jomon sherd porosity using mercury intrusion porosimetry have measured total porosity in the range of 20 to 35%, significantly higher than the 5 to 15% often seen in later, denser kiln-fired stoneware. That porosity was not necessarily a failure of technique. It may have been the technique. And pore size distribution matters as much as total porosity. Random large pores weaken clay. Evenly distributed small pores, the kind left by fine plant fibers, can improve resistance to freeze-thaw damage without fully destroying structural integrity. Fiber diameter, fiber density, orientation during hand building, all variables that affected performance. And across thousands of excavated Jomon vessels spanning millennia, fiber tempering remains remarkably consistent. Not random experimentation, transmitted knowledge. But fiber tempering alone does not explain 10,000 years underwater. Other ancient cultures used it too, and their archaeological survival patterns do not always look the same. So something else may also have been happening. A second mechanism, at a different scale entirely. And this one is stranger. When you fire clay in an open bonfire, no kiln walls, no chimney, no stable oxygen control, the atmosphere fluctuates constantly. Flames consume oxygen, then die back. Fresh air rushes in, the fire flares again. The clay cycles between oxidizing and reducing conditions again and again in a single firing. In reducing conditions, when oxygen is scarce and carbon-rich gases dominate, something happens that modern potters often try to control very carefully. Carbonaceous residues can penetrate the clay body, not only on the surface, potentially into the pore network itself, depositing thin films or residues along void walls, channels, and microcracks. If that happened consistently in Jomon pottery, it may have altered the internal surface chemistry of the vessel, not waterproofing it, not sealing it, but possibly reducing wettability in parts of the pore structure and changing the way water interacted with internal surfaces. Why does that matter? because one of the long-term degradation pathways in low-fired ceramics is not purely mechanical, it is also chemical. Water can re-enter the fired body, interact with incompletely transformed clay minerals, and over very long periods contribute to weakening and alteration. Some researchers discuss this in terms of rehydration and post-firing alteration rather than as one single simple process. Carbon-rich residues may have acted as a partial barrier, slowing some of that interaction. Research on carbon deposition in archaeological ceramics shows that carbon introduced during low-temperature reducing firings can persist for extremely long periods. Jomon potters did not know carbon chemistry in modern terms. There is no evidence they could describe the mechanism, but they may have controlled it in practice. The firing method, open bonfire, vessels placed directly in fuel, rapid atmospheric fluctuation, would have increased the opportunity for carbon-rich residues to penetrate the body. And the thick walls characteristic of early Jomon pottery, sometimes over a centimeter, gave that process more space and more time to work. So now you have two defense systems, potentially operating at the same time, at different scales, against different threats. Mechanical damage from freeze-thaw cycling, chemical weakening from long-term water interaction, both at least partly managed. Modern industrial ceramics solve both problems by firing hot enough to vitrify, turning the clay body into something much denser and more glass-like, sealed, far less permeable. Jomon potters seem to have solved related problems at much lower temperature, using physical behavior they could not name, but had clearly learned through repeated observation. And none of this happened in isolation. Behind those vessels stood a system. The Jomon period runs from approximately 14,000 BCE to 300 BCE. That span is so vast, it is difficult to process. The entire history of agriculture, writing cities, empires, and industry fits inside that window with room to spare, and throughout it, the people of the Japanese archipelago made pottery continuously while remaining outside full agricultural systems until very late in the sequence. That should stop you. Many of the world's major pottery traditions are closely tied to farming, storage, food processing, and settled life. The Jomon are the great exception. Complex hunter-gatherers, fishing, shellfish collecting, nut harvesting, deer hunting, and making some of the most sophisticated early pottery on Earth. The evidence comes from shell middens, enormous refuse mounds along Japan's coastlines. The Sanai Maruyama site in Aomori Prefecture, occupied from roughly 3,900 to 2,200 BCE, according to excavation reports by the Aomori Prefectural Board of Education, shows a community of several hundred people, large communal buildings, organized storage pits, massive quantities of pottery in distinct stylistic phases. These were not nomads casually shaping clay between migrations. These were semi-sedentary communities stable enough to develop, refine, and transmit ceramic technology across generations. And that transmission mechanism matters. Without writing, technical knowledge passes through apprenticeship, direct embodied learning. You do not read how to mix fibers into clay. You watch. You feel the consistency under your hands. You learn how much grass to add, how long to dry, how deep to bury the vessel in the coals. It is a fragile system. If a generation is lost, through disease, migration, conflict, disruption, the knowledge can go with it. And yet the technology shows remarkable continuity, across thousands of years, across hundreds of kilometers. The fiber tempering persists. The open fire method persists. The thick wall construction persists. Regional variations exist. The flamboyant flame-style vessels of Middle Jomon in Niigata look nothing like the simpler cord-marked pots of early Jomon in southern Kyushu. But the underlying material logic stays surprisingly consistent. That suggests a network, not a centralized school, but overlapping communities of practice where techniques spread through kinship, exchange, imitation, and seasonal gathering. And one detail reveals just how deep Jomon material knowledge may have gone. At Torihama in Fukui Prefecture, a waterlogged site preserving organic material with extraordinary fidelity, excavators found evidence associated with lacquer use dating to approximately 12,600 years ago, among the oldest evidence of urushi anywhere in the world. Lacquered objects themselves, ornaments, combs, textiles, appear in the record around 9,000 years ago at Kakenoshima in Hokkaido. Together, they document a lacquer tradition older than any other currently known. Lacquer requires harvesting sap from specific trees in specific seasons, processing it carefully, applying it in controlled humidity, because urushiol only cross-links into a waterproof film under the right moisture conditions. They were handling polymer chemistry without hygrometers. People who understood lacquer curing, seasonal sap harvesting, and carbon-rich low-fired clay without a single written formula were not primitive. They were running a materials tradition transmitted orally across hundreds of generations. The pottery at the bottom of Lake Biwa did not survive by accident. It survived by design. A design embedded so deeply in practice that its makers may never have needed to state it as theory. Now, let us see how that design holds up against modern industry. 4 metrics. Jomon-style earthenware versus modern industrial ceramics. No romanticism, no industrial bashing, just a fair scorecard. Compressive strength. Modern stoneware fired at 1,200 to 1,300 degrees Celsius can reach 50 to 100 megapascals. Some technical porcelains exceed 500. Jomon-style earthenware fired at 600 to 800 degrees is far lower, with experimental reproductions suggesting roughly 5 to 20 megapascals. Modern wins by an order of magnitude or more. If you need a vessel for mechanical loads, industrial piping, engine components, structural tiles, Jomon clay does not compete. Full stop. Water impermeability. Modern glazed stoneware and porcelain can have water absorption below 0.5%, essentially waterproof. Jomon earthenware can absorb 15 to 25% of its weight in water. For storing liquids without loss, modern ceramics dominate completely. That is why advanced ceramic traditions kept pushing toward higher firing temperatures and glaze technology. The demand for waterproof performance drove the innovation. Freeze-thaw durability per unit of firing energy. This is where the picture changes. Not absolute strength, not impermeability, but how much durability you get for the amount of energy invested in firing. Modern frost-resistant ceramics usually require temperatures above 1,100 degrees Celsius, often above 1,200, to vitrify and seal pores. A modern gas-fired kiln running at 1,250 degrees for 12 hours can consume enormous energy per cubic meter of capacity, according to figures from the European Ceramic Industry Association. Jomon bonfire firings, reaching 600 to 800 degrees for 2 to 4 hours, consumed only a fraction of that energy, possibly 1/10 or less. Precise comparisons are difficult, but the order of magnitude difference is clear. And yet, despite that tiny energy input, Jomon pottery achieved long-term environmental persistence through a different pathway. Pore architecture, rather than vitrification. Not as strong as a modern frost-proof tile, not as waterproof, but durable enough to persist for extraordinary spans of time in certain conditions. Durability achieved per joule of firing energy? That is where the Jomon system becomes genuinely impressive. Environmental persistence. This is the metric that launched the video. The archaeological record is the dataset. Jomon pottery survives in enormous quantities, with hundreds of thousands of recovered sherds across more than 100,000 documented sites, according to the Agency for Cultural Affairs of Japan. Modern industrial ceramics have not existed long enough to generate a comparable archaeological record, though laboratory testing suggests excellent long-term durability as well. So the honest answer is this: both last, but they last through fundamentally different strategies. Modern ceramics resist the environment by sealing it out. Jomon ceramics resist the environment by accommodating it, absorbing water, distributing stress into void spaces, and possibly using carbon-rich pore chemistry to slow internal degradation. A submarine survives the deep ocean by creating an impervious steel shell. A fish survives the same ocean by living inside the environment and managing it. Neither strategy is wrong. They solve related problems through opposite philosophies. And modern materials scientists are still working with the same principles Jomon potters seem to have discovered through practice. The principle behind Jomon pore architecture, controlled, evenly distributed voids that absorb thermal stress rather than simply resisting it, now appears in research on lightweight refractory ceramics, thermal shielding, and engineered porous materials. Modern engineers are arriving, through modeling and testing, at structural ideas that Jomon potters reach through repeated hands-on refinement. 14,000-year-old hunter-gatherer pottery informing 21st century materials logic. That is not nostalgia. That is engineering. And if you want to try part of that system yourself, you can. You do not need a kiln. That is the whole point. Jomon-style pottery is one of the most accessible ceramic traditions on Earth. A small number of potters and experimental archaeologists are still actively keeping elements of it alive. Here is the system. Step 1. Source your clay. You want secondary clay, clay transported by water from its geological origin and deposited in riverbeds, floodplains, or lake margins. Secondary clays contain natural impurities, fine sand, iron oxide, organic matter, that can actually help in low-fire pottery. They are often more forgiving than highly refined commercial clays. If you are near a river with exposed clay banks, you can dig your own, where legal and safe. Look for soil that is sticky when wet, plastic enough to roll into a coil without cracking, gray to reddish brown. Let it dry. Crush it. Soak it in water. Strain it through mesh to remove stones and debris. Step 2. Temper it. This is the step that separates Jomon method pottery from just playing with mud. Chop dry grass, straw, or pine needles into segments roughly 1 to 3 centimeters long. Mix them into the clay at approximately 15 to 25% by volume. You want the fibers distributed evenly but not so dense that the clay stops holding shape. Knead thoroughly. The clay should feel like dense bread dough with visible strands throughout. Step 3. Build your vessel. Coil construction. Roll the clay into long ropes. Stack them in rings. Ice smooth the joints. No potter's wheel. Walls should be thick, 8 to 12 millimeters minimum. Thin walls fire too fast and may lose some of the internal carbon effects and structural tolerance that protect the vessel long term. Dry slowly, several days minimum. Too fast and the exterior shrinks ahead of the interior. Cracks. Keep it in shade, out of wind. Turn it periodically. Step 4. Fire it. Build a wood fire in a pit or on flat ground, where legal and safe to do so. Burn it down to a substantial coal bed. Preheat your vessel near the fire, not in it, for at least an hour to drive out residual moisture. Then nestle the vessel directly into the coals and pile wood around and over it. The key is fuel contact. You want the vessel buried in combustion material so reducing conditions can form around it, driving smoke and carbon-rich residues into the pore structure. Maintain the firing for 2 to 4 hours. Let everything cool naturally. Do not pull the vessel out while it is still hot. The mistakes that ruin it. First, using commercial clay bodies designed for enclosed kiln firing. Too refined, too dense, too homogeneous. They often perform poorly in bonfire conditions. Second, the wrong fibers. Synthetic materials. Plastic-coated straw, heavily processed plant matter. Use raw, unprocessed, natural material only. Synthetics release gases that create bad porosity patterns and chemical residues. Third, and this destroys more attempts than almost anything else, rushing the drying phase. Build today, fire tomorrow, lose everything. Water trapped in the core turns to steam during firing and can blow the wall apart from the inside. 4 to 7 days of slow drying at ambient temperature, minimum, for 10 millimeter walls. Where to learn more? Experimental archaeology programs at Meiji University and the National Museum of Japanese History in Sakura, Chiba Prefecture, have offered workshops or public demonstrations related to Jomon reproduction methods. Cost? Almost nothing if you use local clay and local fuel. A bag of suitable secondary clay from a supplier can cost $10 to $20 and make several vessels. No kiln, no electricity, no gas line. But here is the honest limitation. Jomon-style earthenware is not reliably food safe by modern standards without additional treatment. Its porous body can harbor bacteria. It is not waterproof. Liquids can seep through, and it cannot handle thermal shock from a modern stovetop the way modern cookware can. For cooking over open flame, which is how Jomon vessels were originally used, it can work. Thick walls heat slowly and evenly. For storing dry goods, for planters, for decorative use, outstanding. For holding drinking water or cooking on a modern range, use modern ceramics. And that leads to the bigger question. If low-fire, fiber-tempered clay can be this persistent, why did the world move away from it? If low-fire, fiber-tempered clay is this durable, why did almost every ceramic tradition eventually move beyond it? The answer is not durability alone. It is throughput. A bonfire firing produces a handful of vessels at a time. Failure rate is high. Even skilled practitioners can lose 20 to 40% to thermal shock based on experimental reproduction data. Every vessel is unique, shaped by hand, dried for days. Fired in a variable open fire. The process cannot be easily automated, standardized, or accelerated without changing the very material properties that make it special. A modern tunnel kiln can produce thousands of identical tiles per hour. Failure rate below 1%. The product is waterproof, food safe, dimensionally precise, endlessly reproducible. For a civilization trying to house, feed, and equip billions of people, the modern kiln is not optional. It is necessary. The displacement of low-fire earthenware was not a conspiracy. It was not stupidity. It was optimization. Scale a technology from village use to industrial production, and you optimize for consistency, speed, and cost per unit. Low-fire bonfire pottery scores poorly on all three. High-fire kiln pottery scores well. The market chose accordingly. What got left behind was not pottery. It was a philosophy. The idea that a material can survive by accommodating its environment instead of sealing it out completely. That philosophy does not scale easily. But for applications where longevity, resilience, and low-energy production matter more than volume, garden pottery, architectural ornament, art objects meant to last centuries, The Jomon approach still has something to teach. Industrial economy optimized for throughput. Jomon economy optimized for persistence. Both rational, neither complete. That vessel in the sediment of Lake Biwa, mapped by a robot, dated by radiochemistry, analyzed through modern archaeology, was shaped by someone who knew none of those words. No concept of porosity gradients, no language for hydrophobic surface chemistry, no theory of crack deflection. But they knew the clay, the way a carpenter knows wood grain, through hands, through repetition, through failure, through hundreds of generations of someone showing someone else how to mix, shape, dry, and fire. The knowledge was not written because it did not need to be written. It was embedded in practice, in the muscle memory of kneading fibers into river clay, in the judgment of when the coals were ready, in the patience of slow drying. We look at that vessel and see a primitive object, a crude container made by people without technology. But the evidence points somewhere else. It suggests that these objects addressed two of the hardest long-term challenges in low-fired ceramics, freeze-thaw damage and water-related chemical alteration, at the same time, at low temperature, with almost no industrial infrastructure, or using plant fibers and wood smoke. Controlled porosity. The same broad principle protecting the highway you drove on this morning. One version patented in the late 30s. Another practiced many thousands of years earlier. By people we still call primitive. Maybe the word we should retire is not ancient. Maybe it is primitive. Here is what I want you to do this week. Go outside. Find a riverbank, a safe exposed soil cut, a place where earth is visible and legally accessible. Pick up a handful of soil. Squeeze it. Does it hold its shape? Sticky? Plastic? Cohesive? If it does, you may be holding the same kind of material that lasted 10,000 years at the bottom of a lake. If it crumbles, you have sandy soil. Keep looking. Now drop one word in the comments. What is the oldest handmade object in your house right now? A bowl from your grandmother, a tile from a demolished building, a clay pot from a flea market. One word, one object. Next week, we are going to a desert, a place where people built refrigerators out of dirt and wind 2,000 years before electricity existed. The Yakchal, Persian ice houses. And the thermodynamics are going to break your assumptions about what low-tech really means. Subscribe. I will see you there.